Hey guys, Audrey here. Let's do group work 7. So first of all, I want to find the critical values of this thing, which means I need to find the derivative. So I'm going to start off by rewriting this as x minus 4 times 3x minus 4 to the 1/3. So then f prime of x is 1 minus 4 times 1/3 times 3x minus 4 to the negative 2/3 times 3. I'm doing like a mini chain rule there. And I can see that 1/3 times 3 is equal to 1, so I can cancel those out. Now this is not addition or subtraction, this is all multiplication. This is like 4 times 1/3 times 3x minus 4 to the negative 2/3 times 3. So order doesn't matter, nothing is stuck to itself, nothing is stuck to each other. 1/3 times 3 is 1, that's okay, I can do that, this is all multiplication. I also know that I need to get rid of negative exponents when I am simplifying, so I'll have 1 minus 4 over 3x minus 4 to the positive 2/3. Okay, now that 4 stays on top because it's 4 times that thing. That 4 is in the numerator, it's not 1/4 times, it's 4 times. The 4 is not to the power of negative 2/3, it stays up top. Now, I want to find where f double prime is equal to 0. And in order to do that, I'm going to take this whole thing and set it equal to 0. And I'm going to start off, I want to isolate x, so having x on a side of the equation with no addition or subtraction is a good plan. So I'm going to start off by adding this 4 over 3x minus 4 to the 2/3 to both sides, so that I have 1 is equal to 4 over 3x minus 4 to the 2/3. Now having x in my denominator, also not a great plan. So I'm going to multiply that 3x minus 4 to the 2/3 over. So I get 3x minus 4 to the 2/3 is equal to 4. Now this might be a little bit of a confusing place for you. How do you get rid of that exponent? Well, what we saw in class is that if I have something like x to the a over b is equal to a constant or whatever, to get rid of the exponent, I just have to flip the fraction. So I'm flipping my fraction over. Now, a thing that we have to be careful about is when we do that, am I doing like a square root? So if that a is even, I have to do plus or minus. So in other words, over here, what I can do is put this to the power of 3 over 2. But when I do that, that 2 on the bottom is like a square root, so I have to do a plus or minus. So I end up with 3x minus 4 is equal to plus or minus 4 to the 2/3. I'm sorry, 4 to the 3 over 2, my bad. 3 over 2, which is plus or minus 8. So this is a little confusing because now I have to separate this into 2 different equations. So I get 3x minus 4 is equal to positive 8, which gives me 3x equals 12, which gives me x is equal to 4. Or I have 3x minus 4 is equal to negative 8, which gives me 3x is equal to negative 4, which is equal to, gives me x is negative 4/3. So those are my 2 critical values that I get right here. Now, another way that you could have thought about this, so this is what we did in class. We did this a while ago, but we saw how we could like do that power of b over a. But another way that you could have thought about this would be thinking of it as if it's the cubed root of 3x minus 4 squared is equal to 4. And we know to get rid of a cubed root, we just cube both sides. So then I would get 3x minus 4 squared is equal to 64. And now to get rid of a square, I know I square root both sides, and then it's really obvious that I have that plus or minus. So I get 3x minus 4 is equal to plus or minus 8, which notice is the same thing that we had over here. Now, I didn't see this method in class. We saw the b over a method in class, but either one is perfectly reasonable. And maybe the second one helps you to understand a little bit better what we're doing with that plus or minus. Okay, so then we also want f prime does not exist. And f prime does not exist comes from when my denominator equals to 0. Powers don't matter because 0 to any power is still just 0. So this gives me x to the positive 4/3. So my critical values here, I have 3 of them. Our x is equal to negative 4/3, positive 4/3, and 4. And that is my final answer to this question. All right, let's look at question 2. Now I've already written the solution to this, but I'm just going to talk you through it. So first we are asked to find intervals of increase and decrease in local extrema. So I'm going to be doing the first derivative test and the test for increasing, decreasing. The first thing I did was took the derivative, and then I found the greatest common factor of that derivative, which was x squared plus 1 to the negative 1/2. It was the thing that showed up on both sides. We took the lowest power. When I factored it out, you'll notice how to determine what's left in the first. Remember, we're always doing the difference of the exponent. So here you have that 1/2 minus negative 1/2. That shows me that the thing that's left inside is just x squared plus 1. Now I expand and combine like terms on the inside, and then I get rid of my negative exponent. So I don't want any negative exponents left over. Okay, now in the next step you'll see I actually factored the numerator. So sometimes it's a little bit challenging to factor non-monic quadratics. In other words, quadratics where it's not just x squared, it's some number times x squared. So I'm just going to briefly talk about that. So I have 2x squared minus 3x plus 1, and I want to factor that thing. So what I'm going to do is multiply this 2 and 1 together to get 2. So I want two numbers that multiply to be positive 2 and add to be negative 3, that negative 3 that's in the middle. And so it's clear that those two numbers in this case are negative 2 and negative 1. So then I can take this and separate that negative 3 into a negative 2 and a negative 1. So I'm taking negative 3x and having negative 2x minus x plus 1. And then I can factor by grouping. So here I can factor out the 2x, and here I can factor out a negative 1. So I get 2x times x minus 1 minus 1 times x minus 1, which gives me 2x minus 1 times x minus 1. So that's just a little brief review. The reason that we want to factor that thing is because that's going to make it so much easier to set it equal to 0, which I did in the next step. So here I have f prime equals 0, and I can immediately see that. That gives me x equals 1/2 and x is equal to 1. Where it doesn't exist, x squared plus 1 equals 0, that never happens, because in order for that to happen, we would have to have x squared be a negative number, which we know isn't possible. So then I set up my table of values. I picked a test value on each interval. That 6 looks like a 6. It's supposed to be a 0.6. 1/2 is 0.5, so I need something between 0.5 and 1, so I went with 0.6. Then I'm plugging those values in to the second derivative. Now, an important thing to note about the second derivative is that x squared plus 1 to the 1/2 is always positive. So my denominator is always positive. Having that numerator in the factored form makes it really easy to plug this in. So when I plug in 0, I'm just looking at 2 times 0 minus 1, that's negative, 0 minus 1, that's negative, and I can see that it's positive there. In the same vein, I can see that it's negative at 0.6 and positive at 2. So 2 times 0.6, that's 0.3 minus 1, that's negative. That's negative, and I think that I just said 2 times 0.6 was 0.3, I don't know if I said that out loud, is 1.2, my bad, minus 1 is positive, so then 0.6 minus 1 is negative, and we end up with a final negative value. Same with 2, I can plug that in and see positive, 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 and that is positive. So I'm able to conclude that it's increasing on negative infinity 1/2, union 1 infinity, and it is decreasing on 1/2 1. Then, because we're also asked to find the local extrema, I see that at 1/2 it goes from up to down, so that's a max, and at 1 it goes from down to up, so that's a min. Then I'm going to go and plug both of those values into f. To find y values, we always plug into the original function. So I plug in and see that there is a max at -5 root 5 over 4. And there is a min at 1 -2 root 2. So that is my final answer to question 2. So for question 3, I also have the solution already written out for us. It's pretty straightforward problem as long as you remember to simplify the derivative. The derivative I took, it's just a simple power rule, but then I need to simplify, and the simplification requires finding a greatest common factor that has an exponent that is fractional and negative, and sometimes that's challenging. So we're always doing the difference of exponents. So to figure out what's left over when I factor that out, I'm doing 2/3, what's inside, minus -1/3, the thing I factored out, to see that the power of x is 1. I also want to make sure to get rid of my negative exponent that's left right here. So I bring it down to the bottom. The 10 does not go with it. They are not stuck together. This is 10 times that thing. So it's 10 stays on top, that 2 minus x stays on top. So then I get when f prime equals 0, that happens at 2, and f prime does not exist. That's division by 0. That happens when x is equal to 0. So I plug in those values that I got to my original function because I'm doing the extreme value theorem here. Why am I doing the extreme value theorem? Because I'm asked to find the absolute extrema on a closed interval. And when we're asked absolute extrema, closed interval, that's always the extreme value theorem. So I plug them back in to the original function so that I can find my biggest and my smallest y value. So I'm plugging in the endpoints, my 0 and 3, and my critical values that I found. That 2 was on the interval, that 0 was an endpoint. So they are both values I'm going to be plugging in. I plug them in to get my global min at 0, 0, and my global max at 2, 18 times 2 to the 2/3. You do not have to simplify that thing. You can leave it like that. I know it's a little bit gross, but I'm not expecting you to simplify that to get 18 times 2 to the 2/3. You're welcome to leave it in that gross form. The only thing that you're not allowed to do is put 28.57. That is not an exact answer. I want exact answers, so no decimals. Okay, so that was our question about the extreme value theorem. Now we're going to actually write out our answer again. Second derivative test. Second derivative test tells me that I need to start by finding my critical values. So I have a product rule here. That's f, that's g. So I'm going to do f prime of x is the derivative of the first times the second plus the first times the derivative of the second, and that has a little chain rule there. And then my greatest common factor, because I'm looking for critical values, I want to simplify this, is just 2x plus 9 cubed. So I'm going to factor out that 2x plus 9 cubed. And what I have left in my first term is 2x plus 9. And what I have left in my second term is x minus 3 times 4 times 2. Then I expand. So I'm going to multiply that 8 through and combine like terms. So I'm going to have 2x plus 9 plus 8x minus 24, which gives me 2x plus 9 cubed, 2x plus 8x, that's 10x, minus 15. And if I want, I can actually factor a 5 out of that 10x minus 15, but I don't have to. I can leave it like that. It's really straightforward to find my critical values from there. So f prime equals 0. That happens when 2x plus 9 equals to 0. So that's x is equal to -9 over 2. And it happens when 10x minus 15 is equal to 0. So that's x is equal to 15 over 10, which is 3 over 2. So I got these two critical values. I don't have to think about where f prime does not exist for two reasons. One, well, it always exists. There's no division. But two, because for the second derivative test, it is not useful. So we can just say not useful for the second derivative test. Okay, Now I'm going to plug these values in to the second derivative. And in order to do that, I need a second derivative. So now I'm going to take f double prime of x, and I'll have 3 times 2x plus 9 squared times 2 times 10x minus 15 plus 2x plus 9 cubed times 10. Now, I do not need to simplify this. I can leave that in this form here. But simplifying will make it easier to plug in. So no need to simplify. But it will make it easier to plug in. So I'm going to actually simplify just because I'm kind of doing this in my head here. So I'm going to end up then with, I'm going to factor out just 2x plus 9 squared. Yes, there's a factor of 2 on both sides. There's also another factor of 5. So I technically have a factor of 10 that I could also factor out. But because I'm just doing this to simplify, I'm just going to pull out that 2x plus 9 squared. So then I'll have 6 times 10x minus 15 plus 10 times 2x plus 9. And now I want to expand and combine like terms. So that's 60x minus 90 plus 20x plus 90. And I can see that what's left inside there is just 80x. So it's going to be really easy to plug those critical values into this because I'm just looking for a sign. So this though, that said, this was not actually necessary. It depends on how comfortable you are with simplification. So now I'm looking at f double prime of negative 9 over 2, and I can see that that's actually equal to 0. And so if it's equal to 0, that means the second derivative test is inconclusive. And then I'm going to look at f double prime of 3 over 2. And 3 over 2 squared is clearly positive, and 80 times 3 over 2 is also positive. So this is greater than 0. So it's positive, so it's happy, which means that I have a min there. So I have a min at x is equal to 3 over 2, which I'm going to then plug in to my original function. So I have 3 over 2 minus 3 times 2 times 3 over 2 plus 9 to the 4th. 3 over 2 minus 3 gives me a negative 3 over 2, and then that's times 12 to the 4th, which I'm going to actually pause and plug into my calculator, which gives me a negative 31,104. So my min is at 3 over 2, negative 31,104 for my final answer here. And then we also have the second derivative test is inconclusive at x equals negative 9 over 2, which is also an important part of the answer because we were told if the second derivative test fails, does not apply, simply state this. So here it just failed, it was inconclusive. All right, one problem left to do here, guys. We are almost done. Intervals of concavity and inflection points of this thing. Let's get through this fast. F prime of x, the derivative of the first times the second, plus the first times the derivative of the second. Now, I want to simplify this to find my derivative, which means my second derivative, which means we want to have the e part times the polynomial part. I'm not looking for a greatest common factor here. I'm just factoring out the e. So I'll have x squared minus 12 plus 2x, which I'm going to rewrite as x squared plus 2x minus 12. And then f double prime of x is e to the x times 2x plus 2 plus e to the x times x squared plus 2x minus 12. And I'm actually going to erase that and redo it because I did it backwards from how I normally do it. So derivative of the first, e to the x squared plus 2x minus 12, plus the first times the derivative of the second. Simplify by factoring out that e to the x, my greatest common factor. and then the polynomial part is what's left over. So now I want to combine my like terms, so I can combine those 2x, and I can do negative 12 plus 2 to get e to the x times x squared plus 4x minus 10, which I can factor. I want two numbers to give me, multiply to give me negative 10, and add to give me 4. So 1 and 10, not going to do it. 2 and 5, not going to do it. Which kind of brings us to, is there anything that's going to do it? So at this point, it might be a good idea to check and see if this thing actually factors. And remember, to check and see if the thing actually factors, we're looking at b squared minus 4ac. If that is less than 0, it does not factor. So let's check. 16 minus 4, or rather 4 squared. So 4 squared minus 4 times 1 times negative 10. And guess what? That is greater than 0. So this would be a good time to bring the quadratic formula into play. So we're going to do the quadratic formula here to find our values where this equals to 0. So I'm not going to factor that. We're going to say f prime is equal to 0. We'll deal with that quadratic formula a bit in just a second. This happens when e to the x equals 0, which never happens, or when x squared plus 4x minus 10 is equal to 0. So now we're going to use our quadratic formula, which is the opposite of b plus or minus the square root of b squared minus 4ac over 2a. So this gives me x is equal to the opposite of b, that's negative 4, plus or minus the square root of 16 plus 40 over 2. So we kind of have some gross values here. That's okay. We've seen gross values. You guys saw gross values in class. You saw them in your web work. So this gives me negative 2 plus or minus the square root of 56 over 2. That I'm going to now use for my intervals of concavity. So here I'll have my first interval, negative infinity, negative 2 minus root 56 over 2, negative 2 minus root 56 over 2, negative 2 plus root 56 over 2, and then negative 2 plus root 56 over 2. I wrote that wrong. The line is only here. Root 56 over 2, root 56 over 2. Comma, infinity. Okay, so these are my intervals. Now I'm going to pick a test value, and I'm going to plug them into f double prime. Okay, so I just plugged them into the calculator. Having these as decimals is going to make it much easier for us to pick our test values. So here I'm going to pick negative 6. Here I'm going to pick 0, and here I'll pick 2. So then I'm doing f double prime of these values. So f double prime of negative 6, that's e to the negative 6, which is a positive value, times negative 6 squared plus 4 times negative 6 minus 10, which we can plug into our calculator. So that's 36 minus 24 minus 10, which gives us a positive value. So that means here we have a positive number. This is concave up and happy. Then we'll do f double prime of 0, and we get e to the 0, which is 1, times negative 10. So that's positive times negative, which gives us a negative value. So now it's sad. And then we're going to look at f double prime of 2. So that's e squared. So that's going to be 4 plus 8 minus 10. So we're back to positive times positive, which gives us a positive value. So this is happy again. So here we have that this is concave up on negative infinity, negative 2 minus root 56 over 2, union negative 2 plus root 56 over 2, infinity. and it is concave down on -2 minus root 56 over 2. Oops. To -2 plus root 56 over 2. And that is my intervals of concavity. And both of those values represent inflection points because concavity does indeed change at them. So here I have inflection points at x is equal to -2 minus root 56 over 2, and x is equal to -2 plus root 56 over 2, which I want to plug in to my original function. So the answers are going to be a little bit gross looking, but we've seen that gross looking answers are okay. So this is going to be f of -2 minus root 56 over 2. That gives me e to the -2 minus root 56 over 2 times -2 minus root 56 over 2 squared minus 12. And then f of -2 plus root 56 over 2 is equal to e to the -2 plus root 56 over 2 times -2 plus root 56 over 2. So the longest part of this problem is actually writing this out, minus 12. Okay, that is therefore my final answer. I'm not going to rewrite that because, like I said, it took a really long time. That's my x value. Those are my y values of my inflection points. And we would need to plug those into our calculators to get decimal versions if we needed to graph this thing so that we could have an idea as to where those things stand. And that is finally our last problem. We're done. Yay. Bye, guys.